Okay, so here we have the first Beanie's simplified schoolgirl circuit built for an actual student, for an actual science fair project, and thanks to the assistance of John Bedini through me and the one that I built a long time ago. So it's a basic setup here with just one transistor, two diodes, a neon bulb, a resistor, and then we have a 1-to-1 coil. So this coil does not step up or step down the voltage. We have a 12-volt battery on the front end. This is the supply. This will supply approximately 2 to 5 watts of energy to this circuit and get this motor to start running. This motor is also a generator, and as such, the magnetic flux and all of the magnetic fields as they break causes a high voltage spike to be sent to this battery. There's very little current in either end of this circuit, but especially on here, we're not using current to charge the battery. We're using those high voltage spikes to cause a non-equilibrium steady-state flow of energy from the space-time continuum. Okay, so basically we're curving space-time in the local sphere right here, and causing, with those sharp gradients, an open system of thermodynamics, where the open system of the universe will actually come in and cause this battery to charge up before this one's all the way down. So let's demonstrate. First we have the front end battery sitting at a voltage of 1243. Okay, and we have the battery that we're going to charge up some more. It's actually already a little higher, 1251. Okay, first I'm going to hook up the motor like that. Okay, it's on, but nothing's happening. We're not consuming any energy right now. We're still at that same 1244, 43, right? Okay, so if I give this just a little spin, we'll notice the neon bulbs lighting up here. Okay, that's protecting the transistor. Neon bulbs take over 90 volts before that gas will ignite. So what we're seeing here is already a 12-volt battery causing a motor to run and a neon bulb to light up. Let's go ahead and hook it to the battery. And you hear the coil changes its sound. There's less noise coming out of that bulb. The bulb goes out. And now we're going to hook to there. Now we saw this was 54. That's just going to start going up. It's going to take a little bit and this will start accelerating. 55. Let's turn it up a little bit. A little bit more. I hear the magnets got a little louder. And just reduce the resistance from this battery into the circuit so that it'll go up faster. And bumped up to 56. And we let this go for several hours. 57. And then this thing will be well over 13 volts by the time we're done. And we'll see if this one's in the 30s or 20s or 12.2 or 3 or 4. It will go down some because we got this motor running. 58. Yep, it's going up. Okay, so when we get, okay, I'm going to show you something else here with this neon bulb. I'm going to disconnect the battery again. You can see, oh, did I just blow something? It just quit. Oh no, cut. Oh, there it goes. Oh, it's an interesting dynamic. When you change the resistance, you're supposed to make the bulb go kind of dimmer. And it actually, there we go. As soon as it hits a certain point, it goes out completely. So we want right at the beginning of that. See, that's kind of how we can tune it up. Oh, now it's accelerating. Could be that the coil's still getting used to itself. This is the first time we've run it, and we had to make several extensions to the coil to get it long enough to have enough inductance so that the thing would actually run as a motor. It's taken off now, so I'm going to So now we're charging a little bit quicker. It's 12:59. Of course, this thing's pulling on this little bicycle wheel with magnets taped to it. They're all the North Pole facing out. And the bearings aren't so good on this. The whole shaft is turning. So it's definitely got some friction going on here. These crunchy little bearings. It's actually spinning it against the wood. So this is not what you would call a perpetual motion machine. Many people want to call it that, but eventually, for instance, these bearings are not going to last, right? They're not going to keep going forever. And eventually this battery will run out of energy, but even in its discharged state, say at 11 or 12 or 10 volts even, it'll still run this wheel. But you'd have to really flatten this battery for the wheel to actually stop. However, we just want to keep this one charged up from time to time with a regular conventional energy source. This is not the kind where we have a feedback loop that actually is keeping the primary battery charged. There are more elegant and sophisticated circuits from the same guy, John Bedini, who has managed to, in between the pulses of energy coming out of the battery, we're bringing pulses from this coil back into it and causing it to charge itself up. This is the simplified version where we have two batteries and we just pay attention to what happens here. Now what's really important about this is after several charge and discharge cycles of this battery, we're going to notice something about this battery. We're going to notice that the discharge cycles last longer and longer instead of shorter and shorter, which is an amazing fact. That in itself is reason to pay attention to what's going on here. Because if we have a way to charge batteries that is kinder to the battery and actually causes it to charge and have more capacity than the manufacturer said it would when it was new, then we're obviously doing something right here. We're doing something that the battery likes. And all batteries, lead-acid batteries, nickel-cadmium, nickel metal hydride, those kind of batteries, if they're already rechargeable, they can be hooked to this. And this is a 12-volt battery, this is a 12-volt battery. But we can also demonstrate an 18-volt battery charging up. Or we could put two of these in series and have a 24-volt battery. Or put two 18 volts in series and have 36 volts, and it'll still charge it up using the same amount of energy out of this battery. And that proves that we're not taking energy from this battery and simply putting it in here, because anyone who knows about charging circuits and batteries says you can't hook two batteries to each other and get one of them to get higher. They just sort of even out and they both kind of go down. They're not really, that's just not something you do, a 12-volt battery charging another 12-volt battery. But in here what we have is an open system. We have another source. So what we're showing is not something that's 100% efficient by any means. We got loads, losses, we've got heat, we've got resistance. But what we do have, if we can show more energy coming into this battery as it's discharged that we have available for use, then what came out of this battery is discharging into the circuit. We have coefficient of performance greater than 1.0, or over unity. And that's something that this world sorely needs. That's all I got.
Thank you. Jason, what's your last name?
The Green Resorcerer.